it out, for n equals 0, you would have psi 0, so psi 0 of x equals c sine k0 is 0 pi, so 0 times x. And what is sine of 0? 0. So the trivial solution goes to 0. All right, so that really restricts our answer to what ends. All right, so we're ruled out that. So essentially, there is no n equals 0 state. And the ground state is n equals 1. That's the lowest energy state in the study. All right, so what we found out. So let's conclude again. Okay, so your goal, guys, is to go home and get this problem from beginning to end right on your own. All right? This is the problem that you guys have to be able to do beginning to end on your own. Period. The whole way through. Okay. So what we've got is we've got psi n of x equals c sine k n of x, where our kn equals, well, let's just, kn equals n pi over a, and what we know is en equals n squared pi squared. Well, here's what I can do. I'm going to do one other trick. Check this out. For E1, that equals pi squared h bar squared over 2ma squared for n equals 1. So does anybody have any objections if instead of writing all this stuff out, I write en equals n squared e1? All right, so if n is 1, I get all this stuff. Good. I'm well on my way. I've got a nice wave function. Okay, now, but I'm not done yet. I've got a lot of information. I've got quantized energies, and I've got the functional form of the wave function. But what must be true of the wave function to satisfy the Born interpretation of the Schrodinger's equation?
Square must equal.
What is it? The Born interpretation of quantum mechanics is the probabilistic interpretation. Okay, so I have to satisfy the normalization condition,
Which is a equals 1.
Okay, so what am I going to write? Okay, so next, satisfy the normalization condition for the Born Schrodinger picture. This is the Born Schrodinger picture. So how do I write it down? Right here. How am I going to write that down?
Integral.
The integral.
Minus infinity.
Yes. Equals 1. Equals 1. And where am I going to integrate from?
Minus infinity to plus infinity.
Minus infinity to plus infinity. Alright? So I'll write that down. What do we know about the wave functions in regions 1 and regions 3?
0.
They're 0. So when I integrate all the way from minus infinity to 0, the wave function is 0. And then when I integrate from greater than
integrate from.
So this becomes the integral from
0 to a.
0 to a. I'll go c star sine kx times c. I'll sine nkx sine knx dx has to equal 1. All right. C is a constant, and it's a real constant, so c star is real. So this becomes c squared times the integral from 0 to a of sine squared knx dx has to equal 1. Cn here too. So the Cn in front of each. I should have done that from the get-go.
So if you're in the second solution, you kind of get the.
What's that?
So if you're in the second solution, you also get rid of the I. So the answer's kind of.
Okay, well, this you can do this. There's no complex number here, so.
Right. But if we picked the first solution, it would have been. Right.
Oh yeah, it would have been messier. It would have been far messier. We're going to use it later on. Yep.
Do you want that in C not depend?
What's that?
C will depend on N. Do you want that in there? C is going to be a constant no matter what N. You're going to have another C in later, right?
Right, so what we're going to find out, it could depend on it, all right? So Cn is going to equal a constant. It won't depend upon n, all right? So when you do this integral, you can do this integral. You end up with Cn squared times a over 2 equals 1. Or that Cn equals the square root of 2 over a. So we've normalized that wave function. So for homework, make sure you do that. Okay? How are you going to do it? I'd rather you not just plug it into Maple. I'd like to see you struggle with it, try it by hand, and then eventually you can use Maple if you want. But try different techniques to solve it. All right. So what have we got? We have now come down to this, that psi n of x equals radical 2 over a sine kn, and k is, what did we say it is? It's n pi over a. Where n equals 1, 2, 3 to infinity, and then en equals n squared e1. So what have I just done? I have solved what equation? I have solved Schrodinger's time-independent equation. Okay, now I can go and solve the time-dependent equation. And the things that, again, I want to point out, are these solutions square normalizable? Did I find square normalizable solution to Schrodinger's equation?
Yes.
Okay, yes, because that's what I did under the normalizer condition. All right? Were these separable? Did I do this separable square normalizable? Okay, so put those two things together. These solutions form a complete basis set that have all the properties of a function space, so therefore are Hilbert. Okay? But let's now complete the whole thing. This now leads us to psi n is equal to e to the minus I e n times time over h bar times psi n of x. And psi n of x is 2 over a sine n pi over a x. And so now have I solved Schrodinger's time-independent equation?
Yes.
Yes. How many solutions do I have?
N.
And how many is n?
Infinite.
An infinite. So how many of these? An infinite number. So what do these infinite numbers represent?
Complete basis
A
set.
complete basis set. All right. So here's the kicker. is therefore, what can I say, the most general solution, if I have this great infinite basis set as a solution to Schrodinger's time-dependent equation, what can I say any solution is? So psi, total, general of x of t, I can therefore write as what?
Some constant tempo.
Okay, a constant times that, or do I need more than that? If this is an infinite basis set, that's like I hat and j hat, then I can create any vector as a linear combination of those two bases in the vector space. But now I have what dimensional basis? How many? It's infinitely dimensional. How many of these have an infinite dimension set? So how can I build an arbitrary solution, a general solution? As a linear combination of these. Okay, so how would I write that? That equals, first thing is going to be what? A summation. What am I going to sum over? N. And then what do I need in front of each of these bases? I need a Cn. All right, there's a different Cn. But Cn's in this case represent the, I gave it a name before.
Normalization constant.
No, we already normalized.
Projections.
So projections, Cn's, all right, times e to the minus I ent over h bar, the square root of 2 over a sine n pi over a x. Done.
That's a good one.
So this is the machinery, all right? This is the technique that I'm going to get. And now we're going to solve a problem, all right? Now we're going to solve a problem, and it's in particular, it's 2.2, example 2.2, and it's just like the homework problem that I gave you, which was 2.7, I think. Yeah, just like 2.7. This is how you're going to solve 2.7. So guys, what we just did, all you have to do is repeat it for the different problem that you get. All right, nothing changes. You're going to end up in the same place and things are going to look the same. And really the only thing that changes is the potential V. Does everybody get the idea?
And this was like a simple case because the potential of V just equals 0, right?
Yep. So we're only going to be able to solve for simple things. So what's going to happen is we can solve for this, and then the next easiest potential we can solve for is a harmonic oscillator. Kind of looks like a U.
Yeah.
All right? And then it turns out that things in nature, if they're stable, things in nature that are stable are sitting in stable equilibrium. Right? Like a stable equilibrium is if you give a thing a little push, does it fall catastrophically away from where it was, or does it wiggle about where it was?
Just bubbles.
All right? So I hit this table, does the table just catastrophically fall away? The answer is no. All right? So most things in nature that are stable, you can approximate it as a nice harmonic oscillator potential. Right? So we're going to solve easy potentials like this, and then a harmonic oscillator, and then almost everything else we're going to say it's approximately what of these do. Okay? Okay, but let's now get to this next part. Now, it's important that we look at, well, I'm going to spend next class looking what the spatial parts of these wave functions look like. Well, I guess I should spend a little bit of time now. So here we go. We have, let's look at what psi of x is. Just psi of x is. This is x equals 0, and this is x equals a. All right? So what's the first psi of x that we have that's non-zero? What n?
1.
N equals 1. All right? And so it's going to be sine of 1 times pi over a times x. So let's look at what happens at, let's look at psi 1. Psi 1